to my channel. Recently, I've been doing some interviewing for the team I work for, and I've been noticing that some of the new college grads, they were struggling answering some of the questions that I gave them, not because they don't understand the concept, but maybe because they sometimes feel uncomfortable the way how these questions were presented to them. So I'd like to help, and I decided to start a series of these videos with the theme of interview preparations for these tech company jobs, particularly in the field of hardware engineering and the semiconductors. So today is the first session. I decided to choose the topic of the digital logic design. So, question number 1. Draw the truth table of a NAND gate and implement it with MOSFET transistor. So this is the symbol of a NAND gate. We have two inputs, we call input 1 and input 2, and one output. So if we draw the truth table, we want to tabulate input 1, input 2, and output. So we start with 0, 0, 0, 1, 1, 0, 1, 1. This is an enumeration of all the possible combination of the two input 1 and input 2. So for the NAND logic, we know that when both are one way to think of it is that for an AND gate, the output is only true only if both of the input is true, and if you put a negate in front of the AND gate, you get a NAND gate. So when both the input 1 and input 2 are true, the output should be false. And for the rest of the cases, you should get true. Now let's take a look at how to implement this with a MOSFET transistor. So the idea here is that you don't want to memorize this. You want to have an understanding of how the MOSFET circuit works at the basic level, and try to reconstruct this truth table with the MOSFET. So let's use the symbol with a bubble here to represent for the PMOS. And let's use this symbol to represent for the NMOS. So typically the PMOS connects to the VDD and NMOS connects to the ground. So if the gate logic is a 1, then the NMOS is a short circuit, so it conducts the current. If it's a 0, then actually I'm going to draw in red. If it's a 0 at the input of the NMOS, then it's an open circuit. Then it's an open. And similarly, but in the opposite, works in the opposite for the PMOS. If we got a 1 here, then this is an open circuit. But if we got a 0 here, this is a closed circuit. Okay. So let's take a look at the truth table again. The clue is right here. The output is going to be 0 only if both input 1 and input 2 are true. Now think about it from the circuit standpoint. What kind of configuration would give you this kind of logic? So if it requires both 1 and 2 are true, then 1 and 2 are probably connected in series. And because the output that we desire is a 0, we probably want a pull-down network instead of a pull-up network. Because when the NMOS closes, then the ground pulls it down so that the output gets a logic 0. And unlike this, when the PMOS is closed, the transistor, it's a pull-up network, so it pulls the logic at the output here to the VDD, so you get a logic 1. So getting back to this, because we know input 1 and 2 needs to be connected in series. So we need a series configuration with pull down network. And let's see. So this is our ground, right? And this point is our output. And now let's look at the table. Now let's look at this portion of the table. So a quick observation would tell us that the output is a 1 if at least one of the two inputs is a 0. So we know that when the gate is at the 0, the pull-up network pulls the output voltage up to high, to a logic 1. So, and because that this would hold if at least one of the two input, or in certain cases both the input 1 and input 2 are at the 0, the output would be a 1. So think about it, what kind of circuit configuration would give us that kind of logic? It should be a two parallel configuration. So this would tell us that for on the VDD side, the pull-up network, you should have the PMOS, two PMOS are connected in parallel. Okay, and you group this together. This is your input 1, and you group this together with the gate of the NMOS. This is your input 2. And this is the answer to our question. So you see, when the input is a 1 here, this pull-down network is active. And when the input is 1 here, this pull-down network is active. So the Vout gets pulled down to 0. And when you have a 0 here, then this pull-up network is active. And you have a 0 here, this pull-up network gets active. So if either one of the input 1 and input 2 is 0, then you get a logic 1 here, because it's either one of the pull-up network is active. If both of them are 0, then you still get a logic 1 at the output, because both of them are pulling it up to VDD. Thank you for watching.